Okay, so a quick and dirty introduction to zones. This is certainly not going to be in any way, shape or form a rigorous introduction. It just saves me from typing out an email, basically. So let's just start with a simple function called test1, which does a zone allocation. I'm going to make this a double. I'm going to call alloc, and I'm going to return a, we'll compile this, and we get test1. Okay, so by default, alloc or zalloc, alloc, remembering that zalloc is an alias for zalloc, zalloc for zone allocation, alloc being an alias for zone allocation, and in fact, alloc is really my preference. The main reason why is because alloc is sort of emphasizes that whenever you're explicitly allocating memory, you really should be calling alloc. So if you're calling, there are some reasons to call salloc occasionally. There is almost never a good reason to call halloc. So most of your explicit allocation should be from zalloc. Although, as we'll see a little bit later in this video, you really shouldn't be explicitly calling alloc or zalloc that much either. And I'll sort of explain why a little bit later. So here we have alloc, which, if taking no arguments, assumes an argument value of 1. So let me be explicit about this. And the 1 basically says that we want to allocate one of the requested object type. So the object type is a double. So the object will be 8 bytes in size, and the 1 says that we wish for one of these objects. So we get 8 bytes returned. Of course, if we change this to 2 or 4, if it's 4, then we get 4 doubles back, so we get 32 bytes allocated. Okay, hopefully that's clear. If we don't provide any arguments, then as I was saying before, that is the equivalent of 1. So this would mean 1 double, which would be 8 bytes in total. Let's go back to 4 as we had it before. Okay, so it's a reasonable question to ask then. When A is returned from test1, this pointer to a number of doubles that we've allocated, to the start of a number of doubles that we've allocated, where is that memory actually being allocated? And the first thing to keep in mind with zone allocation, the two most important things to remember is that a memory zone is a memory zone. It's a zone that can contain any amount of memory. Its memory capacity grows as required. And the next most important thing to remember about memory zones is that their default behavior is to live on a stack of memory zones. So what I mean by that is that every thread of execution in extempore has its own stack of memory zones. At the bottom of all of those stacks, or at the base of all of those stacks, is what we call the default memory zone. It's just a standard memory zone, but every stack of zones will always have a default memory zone sitting at the bottom. This default memory zone is never destroyed, and its memory is never reclaimed. So any memory that you allocate into the default memory zone is effectively a leak. That memory is memory that you'll never get back. Now, for most practical purposes, for most of you on a day-to-day basis, the thread of execution that you're going to be running your xtlang code in is going to be one of the threads of execution set up by the primary scheme process that you're running in, or I should say the thread of execution set up by the scheme process that you're running in. So that means that in practice, you've got a primary process and a secondary process by default. And by and large, those are the two processes that your two zone stacks will live in, a separate zone stack for each process. Of course, any other processes that you create will also have their own zone stacks, and they will also have their own default zone at the base of those stacks. So what this means in practice is that if I create a bind function called test2 here, what I'm going to do is I'm going to peek at the zone stack so that I'm going to print out the memory zone, the default memory zone that's at the base of the, well, that's not true, sorry. In the case of calling test2, we don't know if we're at the base of the stack. All we're doing is we're peeking at the currently active zone when the call takes place. So we'll call test1 here, and then I'm also going to do a print after the call to test1. Let's compile this function, and then I'm going to call test2 from the top level, or from the scheme primary process. So what we should assume is going to happen here is that we haven't allocated a new zone, and we haven't pushed any zones onto the zone stack, so we should assume that we're going to get the default zone, which is indeed what will happen. So let's call test2, and we see that we have two memory zones printed here. You'll see that the memory zones both share the same address. They're the same memory zone, in other words. We can see that they have a size. As I was saying before, it's important to remember that the size can grow, and it will grow as required. We can also say that they have an amount of free memory associated with them. Zones try and grow relatively economically, so they allocate a larger chunk of memory than they need, and then they use up that memory over time. So they will usually have free memory available to be allocated from. And we can see here that the total amount of free memory between the two calls has decreased. And of course that makes sense because of course we've allocated these 32 bytes for our double, our A variable. So let's just call this again and make sure that this sort of continues to work as we expect it to, and we can see that it does. So we can remember that our free memory at the end of the last call was 480. At the start of the next call it's still this 480, and it's decreased even further to 448. So that's all working basically as expected. This is all being allocated into the default zone, which is the base of the stack of memory zones, and we're leaking into the ether. We're never going to see this memory back. Okay, so how might we avoid leaking memory like this? Well, we need to introduce our own memory zone, and we can do that, we can do that by pushing a new memory zone onto the memory stack, and we give it a starting size. I'm going to say, let's give it 1K of memory default. In fact, if we give it 0, you're going to find that it's going to allocate, I think 1K, maybe 4K even, by default to get started with. But let's just say 0 for the moment. That's going to push a new zone onto the top of the zone stack for us. And then when test1 gets called, that new zone will be the currently active zone. Let's then afterwards pop the zone. And then what we also need to do is we need to destroy the zone, because popping the zone does not in and of itself destroy the zone. And there's a reason for that, which we might not get into today. But if we destroy the zone that gets popped, then it will clean up any memory that we've used. Let me copy these print lines inside before and after the test so we can see the difference between the default zone and the newly allocated zone that we've made. So we compile this and we run test2, and now we have 4 print lines down here. We have our default zone as we had it before, and we can see that here at the top of the call we have 448 free. Then we push a new zone, and then we're going to peek at the new zone. So this is our new zone here. We can see it starts with a size of 0, and it has 0 free memory. Then we call test1. Test1 then allocates these 32 bytes, which means that the zone needs some memory. And as soon as it needs some memory, it goes, I'm not just going to allocate the 32 bytes, because you're almost certainly going to want some more from me. So I'm going to allocate at least 1K to start with. So it allocates 1K, and then it takes the 32 bytes that you've allocated out of the 1K. So after that, we're destroying and popping the zone, so that memory will then be freed. And we can see also that then our default zone, which started at 448, finishes at 448 because that allocation of test 1 has gone into the zone that we pushed onto the top of the stack. But because we destroyed it, like I was saying here, we are now actually reclaiming that memory that we'd used before. So this actually works pretty well. There's actually a sort of a support macro that helps us with this, which is called beginz. And this works exactly the same as what we just looked at. So you can see here we have our default zone. You'll see that this you'll see that the 8B0 is of course the same as the default zone here. It'll always be the same, but you can see the D50 here is not the same. So we're creating new zones and then destroying those zones. We can see, aside from that, the beginz automatically creates a 4K zone for us. But aside from that, same behavior. So 448 here, 448 here, we're not allocating into the default zone, we're allocating into the new zone that we created and destroyed. Okay, so most of the time, this works quite well. We can do a bunch of work in test 1, and then we can clean it all up in one go, which is the kind of behavior that we want from zones. The problem occurs when we do a bunch of work in test 1, for example, and we allocate a whole bunch of stuff in the zone, and then we want to clean up most of that information, but we want to return some part of it. So let's say, for example, we want to do some calculation based on 2 lists. We pass the 2 lists in, we want to do a bunch of munging on those 2 lists, and then we want to return a list. So we pass 2 lists in, and then we allocate and create all of this churn of memory inside the function, and then we want to return an object. So how do we deal with that? Well, the way we deal with this is that memory zones which are lexically scoped, we can see this beginz here is lexically scoped. It goes out of zone after the end here. So this is the equivalent of saying the create new zone or push new zone up the top, and then this is the equivalent of doing the pop and destroy at the end of this lexical mark here. Now what we can also do is that we can actually return that allocated memory. The last expression of the zone can be returned, and that allocated memory can be copied up one zone in the hierarchy. So the way that works is that we pop the zone off the top, then we copy, we do a deep copy of the allocated memory, the zone allocated memory, from the popped zone into the new zone at the top of the stack, or not the new zone, the old zone, but to the zone at the top of the stack. And that's a way then of copying the data from one zone into another zone. You can also actually explicitly ask to copy any piece of information between any 2 zones. But again, I would encourage you to try and use this way of passing information up, because again, by and large, this is actually the kind of form, I guess, that you should be trying to use. So let me give you an example of this. We'll delete this, and then what we're actually going to need to do is we're going to need to allocate it to something. So let's say x here, and let's just say x double to be explicit, and I'm going to return it from the let. We're not going to use it for anything practical, but what we're going to look at here that's interesting is that, so we have the same kind of zoning that we were doing before, but the last expression in this zone is the return value from test 1. And what's going to happen is that we are going to be creating a new zone, of course, and at the end it will be destroyed down here, okay? But before it gets destroyed, the zone allocation that we made in test 1 is actually going to be deep copied up and returned by the beginz, of course, as x here. So the end result of all of that is if we call test 2 again, and we call test 2, we're actually going to find that our default top-level memory zone is again going to start growing. And so we can see this 448 has now grown to, well, free, I should say shrunk. The free memory shrunk from 448 to 416. And that's because while we are allocating into the new zone and destroying the new zone, we're then copying that allocation up. Okay, I should say not the whole allocation. So let's be a bit clearer about that. Let me go b double star alloc something very large and compile. And again, we'll call test2 down here. And again, we can see here that the free has decreased, but we can see that it's only decreased by the allocation of the A here, not the B, because although the B is being zone allocated, it's being zone allocated by the zone we create here, it's being cleaned up by the zone we allocated here. It's only the A that is the return of the test1 that gets copied up to the X and therefore copied into the top level environment. So as I was sort of trying to explain, this is very useful because it means that we can do a whole bunch of memory munging within, whatever sort of depth of function calls we want to make, and then we can sort of percolate up through our returns the small amount of zone allocated information that we actually want to keep, and that gets copied up through this stack. Okay, so as a sort of that's probably confusing enough for everyone for starters. Please send me questions and I'll make another video that sort of explains questions. This is just easier than writing a long email. There's a lot more to this. One of the things I should say is that although we're talking about these zones in a stack form, and this is the most common way for you to interoperate directly with zones is through this stack behavior, there are other ways that zones behave in extempore. One of them, for example, by default, as we were sort of talking about on the mailing list, is xtmx. If we go print line high, and we make this a string, okay, and we see it printed out the bottom here. I should say as well, the shortcut for xtmx, which I also encourage people to use these days, is the $sign. This line here is effectively equivalent to this. In fact, that is really what's going on behind the scenes. There is a zone being created automatically for you behind the scenes for every time you use a dollar or xtmx call. The other place where you'll always be seeing zones in behavior different to the stack allocation behavior is with top-level bind funcs. So when you go F1 here and you have an outer let where you allocate, let's say 10 doubles here, and we compile F1, this memory is actually, it's allocated at compile time. Okay, so these 10 doubles, or this 80 bytes, is actually allocated at compile time. And then every time, so what we can actually do here is if I do a do loop I 10 p set a to, let's just say 0. Okay, this memory is allocated, and then we also do this initialization. All of that happens at compile time. F1 then of course can be called at runtime, but this has all been managed at compile time. Now this also means there is also a zone in effect here. There is a memory zone associated with every top-level bind func, and that's where this memory is stored. Now why that's important is that when you recompile F1, it is actually freeing the memory in the current zone and creating a new zone to store the new memory for you. So this is just another use of memory zones in extempore that happens behind the scenes. One final thing to keep in mind is that, again, generally speaking, you shouldn't really actually have to call alloc as much as you probably think you do, because whenever you do a bind type, like here, we've created a new frog type, okay? Now, inside our frog test, if we want to create a new frog called F1, or let's call it frog1, then really we should be calling the default constructor for frog. Okay, and it's worth remembering, of course, that this is, you know, this nests, right? So if we go, I don't know, frog forest, and we have, you know, 2 frogs. I guess it should be pond, really, shouldn't it? Pond, frog pond, maybe. Let's say we have 2 frogs in the pond, and then we could have a pond test. And the pond, of course, has, you know, 2 frogs in it. Okay. The important thing to keep in mind here is that these calls are all zone allocated. So whenever we're creating these ponds or these frogs using the default constructors, this memory is all zone allocated. And so again, it's your responsibility to clean this up by introducing your own memory zones. Just a final closing comment is we were using the begin Z macro before. Perhaps even more common than using begin Z is actually let Z, which has the same behavior but in a let form. The reason that's useful, of course, is that we can directly allocate, you know, A double, you know, B double in here like this. Let's say we're on return A, and this is kind of a bad example in a sense, because what we're doing here is at the end of this let Z, we're trying to return the A. Well, no, actually, sorry, it's a good example in the sense that at the end of the let Z, the A that gets returned will be copied up to the zone above. So again, you know, if we call let Z here, let Z example, let's just call it A again so that we're not being confusing. And so the memory that's allocated in this let Z, the B is going to be destroyed, but the A will be, the A here, will be deep copied up into the, assuming we call let Z from the top here, it will then be allocated into the default top level zone. So I hope that's not too confusing. It probably is a bit confusing. Just respond in the mailing list, and I'll try and sort of answer any confusion in a follow-up video, but this was just an easy, convenient way of doing a little response. Okay, thanks.